but I'll go ahead and introduce the next speaker, which is Paul Lucey, whose talk is entitled Relative Magnitudes of Water Sources to the Lunar Poles.
And how about the sound check, Ariel?
Sound check sounds excellent. And we're seeing your screen. Great, all set.
Okay. Terrific. All right, so we've been hearing a ton about water today, water ice. I'm going to talk about where it comes from and how we might detect it. Got to say, it's a treat to follow Dave because he and his work and their co-workers' work is a big player in what I'm going to talk about today. So there are a zoo of sources into the lunar poles. This particular slide I've been showing so long ago. We showed it in Gilruth Gym at LPSC when we used to use cave paintings to depict our lunar science. But these sources kind of have two types. There are sort of boutique sources here. The solar system goes through giant molecular clouds occasionally. We pick up some volatiles there. We get some volatiles from the Earth, but the big dogs in the sources of volatiles in the poles are impacts of comets, asteroids, and dust, the sun, and then principally through Dave's work, recognizing that the moon itself is a major supplier of volatiles to the poles. So let's talk about solar wind first. A lot of this comes from Dana Hurley's work. Over time, the solar wind is relatively constant. We've got about 30 grams of protons per second into the entire lunar surface. And if you go over a billion years, that's 10 to the 18th grams. If we assume 1 part per thousand is converted to mobile molecular water, and then another tenth of that makes it to the poles, the total mass of water is 10 to the 14 grams, and getting to equivalent ice thicknesses, that's 30 centimeters of ice in a billion years and about a meter since Orientali. This is Dave and Deborah Needham's contribution, recognizing that volcanism is a big contributor to the potential supply to the poles. The volcanic flux strongly peaked in the Imbrium, but there's a non-trivial mass later in the Ratticinian. So the total mass of water since Orientali is 10 to the 16th grams with a polar ice thickness of about 30 meters. So a pretty reasonable supply of ice to the poles. But the 500-pound gorilla among the three big dogs is impact. Impact has the biggest potential for contributing volatiles to the poles. We looked at this in a number of ways. It's in the abstract. But in the last billion years, that's about 20 meters of equivalent ice thickness into the polar regions. That's based on both impact fluxes and counting the large Copernican craters. Then if we step back to the Ratticinian, the impact flux was about 5 times higher. The duration is about a factor of 2 longer. And that gives us this really major ice thickness of about 200 meters. We step back to the late Imbrium. I'm only talking about the post-Orientali era. This has 100 times the total flux from the Copernicus, and that corresponds to a potential supply of 2,000 meters of water ice in the permanently shadowed regions. So if we sort of sum up this like a scoreboard, so we have 3 periods and we have three teams, kind of peculiar game here. So in the Imbrian period, the potential supply of impactors is, again, 2,000 meters. It declines exponentially down to 200 in the Ratticinian, 20 in the Copernican. If we just talk about single-digit precision, we have, again, a final abundance of about 2,000 meters. Solar wind is a really pretty minor player in this. There's single-digit contributions of meters to the poles, with a final contribution of on the order of 4 meters. And volcanism is in between, a pretty reasonable contribution in the Imbrian, 3 meters in the Ratticinian, and then they didn't get any runs in the Copernican, but a total ice thickness of about 30 meters. So we should talk about losses. That picture on the right, that was a tough one. There was one more inning to go, and it didn't go well. We have more questions than we have answers in terms of losses. We don't really understand very well how well water ice and other volatiles are actually retained promptly after the impact, whether a lot of the volatiles may be lost immediately to space. A lot of questions in terms of losses in transport. We probably have a pretty good feel for exospheric losses, but the surface interactions of actually propagating water molecules from its source point to the poles has a lot of questions. It's possible that a water molecule in its first encounter with the surface may destructively dissociate, and so the polar regions may only be fed by a narrow region at high latitudes. There's a huge question mark about transient atmospheres that have been studied from impact by Dave Stevens, Parvati Prem, others, and also proposed by Dave and Deborah Needham. This is a whole new ball game on transport. Finally, we have very strong losses right at the immediate surface from micrometeorites and sputtering erosions. This basically wipes out solar wind as a contributor. And finally, regolith overturn is often described as a sequestration process, but it's pretty ferocious at the sort of centimeter scale and may actually be a net loss, at least for these superficial sources. So just to talk about current events a little bit. So Ariel Deutsch and the Space Cowboys had a poster earlier this week, and they showed that only pre-Copernican craters exhibit ice detections based on the M-cube results. And this is consistent with loss outstripping supply in the Copernican and may force us to dial down that impact source. But the timing of the ice emplacement isn't really strongly constrained by that. The onset of the permanent shadow could be as late as the late Eratosthenian, and we still get a significant supply. Last year, Lior Rubinenko showed that polar craters on the Moon and Mercury show anomalously shallow depth-diameter ratios, which also correlate with surface ice exposures. These may show that there's a sequestration of ice that's outside the reach of the neutron spectrometers. So here's some terrible tables that address the signatures of volcanism and comet impact. We have some comet analyses by Zhang and Page, the lunar volcanism volatiles from Needham and Kring, and Tony Colapride's L-cross results. But if we condense this down to a simple table and we talk about just the elements, the elemental abundances and not the compounds, there's a very significant difference between the volcanic input and the cometary input. So there's almost, thank you. There's almost an inverse signature here where the cometary input has sort of a high carbon hydrogen and then kind of dribbles off with intermediate nitrogen and almost negligible sulfur. Whereas we have sort of a Nike swoosh in the volcanic signature, negligible nitrogen, but really high sulfur. So it looks like nitrogen and sulfur could be key discriminators between these two sources. And if we throw in L-cross here, again, breaking the compounds down into the elemental masses, the L-cross results kind of have that Nike swoosh-like signature where we have a very high sulfur abundance, but again, a non-negligible nitrogen abundance. So this may show evidence of the presence of both a cometary and a volcanic source. So the takeaways here is that impact is the dominant source. Volcanism is not unimportant, could be looks like 100 times lower if we assume the current retention rates, which might be way off. Looks like solar wind is not a significant long-term source. The micrometeorite and sputtering loss is too high. Sulfur and nitrogen could be key indicators of the presence of volcanism and impact, and L-Cross showed significant quantities of both those elements. The overall water supply appears to be several order of magnitude too high, embarrassment of riches. Is the retention of water and impact overestimated, or are these other losses underestimated? Maybe the cold traps are younger than we think from the polar wander hypothesis of Matt Siegler, or maybe as Lior has pointed out, maybe the ice is just staring us in the face. I think the upcoming missions are going to make huge contributions to this. A lot of sulfur and nitrogen compounds will be detectable by Trailblazer and also by the Viper mission and other upcoming missions. So thank you very much.
Thank you so much, Paul. All right, we have a first question from Bethany Ellman. Curious about what sulfur and nitrogen compounds would we expect in the form of the elements. She's thinking about Lunar Trailblazer, which is from 0.6 to 3.6 microns. What could they detect that might help constrain some of these ideas?
Yeah, thanks for the question, Bethany. So the three major compounds are sulfur, elemental sulfur, H2S, and SO2. We probably would expect elemental sulfur and H2S, but there's enough chemistry going on the surface that we can't rule out oxidized sulfur. Their major action for the SO2 and H2S is in the 4 micron region, but there are weak features in the region of Trailblazer that you can latch onto. Sulfur, we're actually doing a search using WAC data right now to see if we can see a sulfur signature in the illuminated portion of the poles. Sulfur has a pretty high volatilization temperature, and so it should be stable on low temperature, but still illuminated lunar surfaces.
And nitrogen ice or ammonia?
Nitrogen, there are some weak features in the 2 micron region that are very distinct. So you've got a shot there for sure.
Thanks, Paul.
Not nitrogen ice, I meant ammonia.
Okay. We have some more questions for you in the chat, or stick around for the break period, but I'm going to go ahead and move along to stay on time.